Hello, this video will cover periodic table trends along with other general information about the periodic table that is in line with the content associated with a standard introductory high school chemistry course. In this video, we will be discussing the general organization of the periodic table. We will be also discussing the properties of elements and how the periodic table is associated with the different properties as it progresses. And we will be discussing periodic table trends. Chapter 1, Organization. The periodic table is organized in order of increasing atomic number, going from left to right across each row. To review, the atomic number of an element is indicative of how many protons are in that element's nuclei. There are three types of elements on the periodic table, those being metals that are on the left region of the table, metalloids, which are configured like a staircase that split the metals from the nonmetals and often have many applications to the semiconductor industry. And nonmetals are on the right side of the periodic table. So as we can see, the metals are located on the left side of the metalloids, nonmetals on the right side of the metalloids. Each row on a periodic table is referred to as a period. All elements in the same period have the same number of occupied principal energy levels, I should say. Columns on the periodic table are referred to as groups. Elements within the same group often have similar chemical identities and thus properties due to their mutual molecular composition in that they have the same number of valence electrons, or the same number of electrons in their outermost PEL, which are the bonding electrons. Chapter 2, Properties of Elements. What are the properties of metals, nonmetals, and metalloids? To recap, these are the different elements on the periodic table and their distribution to being metals, metalloids, or nonmetals. Another important thing to note is that although hydrogen is on the left side of the periodic table, it is still a nonmetal. Metals. Metals are often good conductors of electricity. This is because they have a sea of delocalized electrons, and since they have electrons that are able to be in motion, this enables them to easily conduct an electrical current. Metals and metallic compounds are very malleable, meaning they can be hammered into thin sheets. Think of aluminum foil. And they're very ductile and can be drawn into wire, think of how aluminum and silver and nickel can be drawn into wire. They're also luster, and since they have a low number of electrons in their outermost PEL, they are prone to losing electrons to become positive ions. Positive ions are called cations. Nonmetals are poor conductors of electricity because they form molecular compounds that have the electrons held in covalent bonding that prevents them from being in motion. Thus, an electrical current cannot be produced. They're often brittle, dull, and gain electrons become negative ions. Since they have a higher number of valence electrons, they are prone to gaining electrons in order to have a full valence shell. And since they are gaining electrons, or they're gaining negative charges, they will become negative ions. In doing so, negative ions are called anions. The first group on the periodic table, or the leftmost column, are called the alkali metals. These are the alkali metals. Not count, and also it's important to note that hydrogen is not an alkali metal. It is a nonmetal. Each alkali metal has one valence electron, meaning it has one electron in its outermost principal energy level. Subsequently, an alkali metal will form a cation with a charge of +1 because an alkali metal will lose its one outer electron, and since it is losing an electric charge, think of subtracting a negative from your algebra class. If you subtract a negative from an integer or from a number, it will become more positive. It will increase. Thus, alkali metals form cations with a positive charge of +1. Alkali metals are also very reactive, and they're usually found in compound form in nature. Think of sodium chloride, which is table salt, or potassium chloride, or potassium bromide. All of these are examples of compounds, in this case ionic compounds, which will be discussed in a future video, that are usually found as compounds in nature. Will react vigorously with water to form H2 and a base. We will discuss this more in our video about acids and bases. Alkaline earth metals are the second most leftward column on the periodic table. They have two valence electrons. Thus, when they form an ionic compound, they will lose those two outermost electrons. Thus, they will become positive ions or cations with a +2 charge. They're also very reactive and, like alkali metals, will form H2 and a base. Although they are not as reactive as alkali metals, but they are still reactive nonetheless. Transition metals do not have as transparent properties as the alkali and alkaline earth metals. Their properties vary to a much greater degree. Something to note that the ions of transition metals, for one, have varying multiple oxidation states. So alkali metals usually only form +1 ions, whereas transition metals often can form multiple different types of ions. For example, nickel can form both +2 and +3 ions. And these transition metals ions are colored. Each transition metal has a color associated with it when it becomes an ion. Metalloids are the elements that border the staircase that we previously discussed that divide the metals from the nonmetals on the periodic table. The properties of metalloids often are intermediary with respect to the properties of metals and nonmetals. These are the metalloids on the periodic table. So boron, silicon, Ge, As, and Sb, and Te are all examples of metalloids. Halogens are group 17. They are the second most rightward group on the periodic table. Each halogen has 7 valence electrons. Let's recall that a full valence shell has 8 electrons, meaning halogens will gain 1 electron in order to have that electrostatically stable 8 valence shell full PEL. Thus, if they are gaining an electron, they will be a negative ion or an anion with a charge of -1. Halogens, like alkali metals, are very reactive, as it is very mainstream for halogens to bond two alkali metals in a 1-to-1 ratio. Think of NaCl or KBr as examples. Noble gases are the most rightward group on the periodic table. They are completely unreactive. Since noble gases have a full outermost principal energy level, they have no electrostatic reason, so to speak, to gain or lose electrons. Thus, they will not be found in compounds in nature. As we've established, they have a stable octet of 8 valence electrons, except for helium, which has 2 valence electrons, though let's recall from the previous video that discussed subatomic particles, which I would advise watching before this, that the first principal energy level has a capacity for 2 valence electrons. Thus, since helium has 2 valence electrons in its first PEL, it is still electrostatically stable because that is the maximum electron capacity for that principal energy level. Chapter 3, Periodic Table Trends. What trends in terms of electronegativity, atomic radii, and ionization energy will be present on the periodic table? First, let's define those terms. Electronegativity refers to the ability of an atom to attract electrons to its valence shell. Atomic radius refers to the distance from the nucleus of an atom to the outermost electron. Ionization energy, or first ionization energy, as we will explore, refers to the amount of energy to remove the outermost electron from an atom's valence shell. Nuclear charge is the number of protons in an atom's nucleus. Coulombic attraction is the attraction between two particles based on their charges and the distance that separates them. If you have taken a physics course, you will learn that Coulombic force is proportionate to the charge of the first particle multiplied by the charge of the second particle divided by the distance that separates those particles squared. You will not have to know that formula on a quantitative level for this course. However, understanding that relationship will help you in identifying the periodic trends that we will discuss. The closer the two charged particles are, will be indicative that they are more attracted to one another. The bigger the magnitude of charge for the two particles will thus increase the Coulombic attraction that those two particles have for one another. All periodic trends are affected by nuclear charge as well as Coulombic attraction. As we've already established, atomic radius is the distance from the nucleus to the end of the atom's electron cloud. Ionization energy refers to the amount of energy required to remove the outermost valence electron from an atom. Electronegativity is the attraction an atom has for the electrons it has access to in a bond. Across a period, atomic radius decreases. The reason for this is because as atoms are observed from left to right on the periodic table, the amount of protons in those atoms' nucleus increases. If the amount of protons in the nucleus of an atom increases, the effective nuclear charge will also increase. If the effective nuclear charge between the atom's nucleus and its outermost electron increases, that would cause the Coulombic attraction to attract the outermost electron to the atom's nucleus. This will thus cause the atom to have a smaller atomic radius. I hope you can see that. Down a group, atomic radius increases. This is because as we add principal energy levels, remember, the period that an element is in is indicative of how many principal energy levels it has. Thus, as we go down a group, the amounts of PE occupied principal energy levels increase. Thus, the outermost electron will be farther from the nucleus as we go down a group. Thus, down a group atomic radii increases. Across a period, first ionization energy increases. The reason for this is because, as we have established, across a period, the effective nuclear charge of an atom in terms of the Coulombic attraction between the atom's nucleus and valence electrons increases. Thus, it will be harder to remove an electron from that atom since you will have to overcome a greater magnitude of Coulombic attraction to do so. Thus, the first ionization energy, or the amount of energy required to remove that outermost electron, will increase across a period. Down a group, first ionization decreases. First ionization energy decreases, I should say. This is because, as we've already established, the amount of principal energy levels, the amount of occupied principal energy levels, I should say, of an element increases as we look down a group. Thus, that will mean that the distance from the atom's nucleus, or the positive portion of it, to the outermost electron will increase. If the distance between two particles increases, then the magnitude of Coulombic attraction decreases. If the magnitude of Coulombic attraction decreases, then thus a lesser magnitude of ionization energy will be required to remove that outermost electron. Thus, down a group, first ionization energy decreases. If we look at this diagram on the right here, we see that as we go left to right across a period, there will be an increase in ionization energy. However, the only time we observe a decrease in ionization energy is when we move from one period to another. For example, if you look at my mouse, helium here is in the first period. However, when it transitions from helium to lithium, which is a transition from the first to second period, we note the sudden decrease in ionization energy. We see this same idea between neon and sodium and argon and potassium and so on. This is because in these sudden decreases, we are moving from one period to another. Thus, there is a decrease in first ionization energy, as we've established. However, when we move, however, when we move across a period, there is a overall increase in ionization energy as we go across a period, which is observed here. I hope that made sense. Electronegativity. Let's recall that electronegativity refers to the ease at which an atom can attract a valence electron to its electron domain. Across a period, electronegativity increases. This is because the effective nuclear charge of an element increases across a period because more protons are being added to the atom's nucleus. If there is a greater effective nuclear charge, there is thus a greater Coulombic attraction between the atom's nucleus and an electron the atom is attracting to its valence shell. Thus, electronegativity increases across a period. Electronegativity decreases down a group. This is because as we go down a group, more principal energy levels, more occupied principal energy levels are added. This thus increases the distance from the atom's nucleus to the outermost principal energy level. This increase in distance between the two particles will decrease the magnitude of Coulombic attraction. Thus, this will make it harder for an atom to attract a new electron to its valence shell since there is less Coulombic attraction. Thus, electronegativity decreases down a group. Fluorine is the most electronegative element. It is the element with the greatest magnitude of electronegativity. This is because it is the element that is the most across from a period, and it is the element that is the highest in its group. Thus, it has the greatest magnitude of electronegativity. Something important to note is that although noble gases are even more across a group, they have very small electronegativities because a noble gas has a full valence shell of electrons. Thus, it is not electrostatically favorable for a noble gas to attract electrons to its valence shell since it is full. Thus, noble gases or group 18 elements have very minimal electronegativities. Another connection I would like to make is that since, as we've discussed, nonmetals have the tendency to form anions and anions gain electrons, it makes sense that as we go across a period, electronegativity increases. Thus, because in order for it to become an anion, it must attract electrons to its electron domain. Whereas metals, which have the tendency to lose electrons to form cations, do not form do not gain electrons easily. Thus, since electronegativity is a measure of how easily an atom gains electrons, metals, or elements on the left side of the periodic table, will subsequently have low electronegativities. That is it for this video covering periodic table organization and periodic table trends. I hope you found this video informative. I would suggest rewatching portions of the video in order to optimize the education value from it. Please view other videos that I have posted that that are informative in chemistry. I will be forming a playlist for all chemistry videos that will cover all content associated with an introductory high school chemistry course. I hope you have a good rest of your day.